if you're asked to do differentiation from first principles, we'll kind of work out what's going on here. But effectively, what we're doing is we know that a derivative is a rate of change, so a gradient. And if we think of different tangents to points, and we build this up, then basically what's happening is if we shrink how far away we're choosing the 2 points and bring the sort of tangents closer and closer together, we're looking at the rate of change of output over the rate of change of input, and we're trying to close that gap. Okay, so the smaller we make this gap, the more accurate we're going to get to the differentiation at the point. And that's basically where this idea of a limit comes in. So a lot of your exam boards will give you this in the formula book, but this is worth knowing and understanding. So effectively, the derivative is the rate of change of y over x, or rate of change of output over input. And so we're looking at f of x plus h plus the small change minus f of x over the small change h. And we're looking at that as h is closed in towards 0. So we're making h smaller and smaller to look at like basically the net effect of the behavior. So hopefully you've seen that before, but we need to sort of just see this in practice now, and the idea of limits. And then we'll do a couple of questions for this. So let's start with just reminding ourselves of what a derivative is very quickly. So for a polynomial, it should be nice and straightforward. Times by the power, drop the power by 1. So I'm going to do a little example off to the side here for you. Quick reminder, f of x is x to the 3 over 2 plus x to the minus 2. And then if we differentiated that, hopefully we're happy. Feel free to work ahead of me. 3 over 2 x to the half minus 2x to the minus 3. So that's the kind of year 12 stuff you did. Another key important thing is the derivative of a constant will be 0. So like x squared and x squared plus 2, they both have the derivative as 2x. Okay, so very well done if you're happy with that recap. But first principles will take this a little bit further. So if you're just asked to straightforward differentiate something, or you need differentiation in a question, in general, you can just differentiate it. It's only if they specifically ask you to use first principles that you have to use that previously defined formula. Let's look at a question that does ask us to do that. So we'll go through this together just to keep things moving, but do feel free to work at your own pace ahead of me and try and get these notes down. So 4 marks, 4 key steps. We'll have to show every step of working because it's first principles. So it's like a show that. And we must use first principles because they've stated it. So let's have a little look. Derive tells us to use every step. Oh no, not again. Knew it would happen. Right. Try and avoid that this session. Apologies. Right, let's get into this question together then. So let's go from first principles. First thing I'm going to write out is the first principles formula, which is there, which is stated, which is given. And we are going to apply this situation to that function. Now, the f of x in this situation was 4x squared minus 1. So it takes an input x, squares it, times it by 4, and minuses 1. But we're not just going to put x into that. We're also going to put x plus h in as the new x as well. So if we start doing that, that is the function that we're going to plug in. So notice that f of x plus h would be 4 lots of x plus h squared minus 1. So you're going to do the difference of them over h, and we're going to take limits. Now, it might help if we firstly manipulate the f of x plus h. So we double bracket expand it, we times it by 4, and we minus 1. And then we tidy it up. Okay. Right, let's have a little look. So there we go, tidying that up. You might be ahead of me already, but very well done. Hopefully we're good to there. And now we're going to do the difference between that and f of x all over h. Here we go. So you're going to, and I would probably bracket this because where it's a subtraction and we've also got minus terms, we want to get this sort of spot on. And this is as the limit as h approaches 0. So again, I've probably said this loads of times, but I never saw limits until I was at university. It's quite an abstract concept, but it's looking at the net effect of the behavior when we take things to the extreme. So we're going to tidy it up, divide, cancel out by h, and see how we go. So a few of those terms will straight away cancel. -1 minus -1 will go. 4x squared minus 4x squared will go. And we're left with 8xh plus 4h squared over h. Cancel the h's where possible. And it's the same as the limit of 8x plus 4h. As h tends to 0, the 4h will disappear. And of course, we get 8x. Now, if you just straightforward differentiated the question, you would have got that straight away. 8x would have just popped out. But this is how you would do it by the first principles process.